Okay, picking up where the audio cut out of the first video I posted, we are looking at Chapter 3, Section 3, trig substitution. And we're focusing on finding antiderivatives of functions that have the square root of a quadratic. And there's some flexibility to the method. Hopefully, through some examples, I'll illustrate. To begin with, we're going to ignore this term of the quadratic. Okay? And it turns out we can always do that. And then by completing the square, we can convert every quadratic, even when this term is included, to one where it's not. And again, I'll give you an example later once we've covered the main technique. So for now, we're going to assume that we're trying to find antiderivatives of functions. They don't fit any of the patterns we already know, and they contain radicals of this form. There are actually three different forms. So the first one, the square root of a squared minus x squared. Okay, so this a squared just represents a positive constant. I write it as a square for two reasons. Number one, it has to be a positive number. In fact, if this number were a negative number, this function would be undefined for all real values. So it wouldn't be very interesting. So we need this constant. In all three of these cases, there's going to be a constant, and we need it to be positive always. So I can force it to be positive by writing it as a square. More important reason, probably, is that the square root of that number is going to play a prominent role in the work that we do. And if I write this number as a square, then its square root is just the symbol a. Okay, so that's the first case. The second one is when we have a squared plus x squared. And the third case, the square root of x squared minus a squared. So the a squared here is positive, but then this minus sign makes it negative. So for example, let me do these in blue. I could have something like the square root of 4 minus x squared, and so a is 2. Or I could have the square root of 17 plus x squared, and then a is the square root of 17. Or I could have, in the third case, the square root of x squared, minus 16. And so a would be 4. Okay, and in each of these three cases, we're going to introduce a substitution. Remember, the name of this section is trig. It will involve trig functions. And in the end, it's going to convert the function we need an antiderivative for to an integral from the previous section, section 2, trig integrals, you remember. And presumably, since we've done our work there, we're experts in that technique. And so if we can convert these back, then we'll know exactly what to do. So let me pause here while I set up some work for us to do. All right, so case one, we have this radical somewhere in the function. The rest of the function is just algebraic. There's actually no trig expressions in the function, no exponentials, no logs. It's just an algebraic function that includes this radical. Okay, so here's what we're going to do. We're going to substitute like we've been doing, only it's a little different substitution. That is, I'm going to replace x. Normally, we pick a function of x and we let u, our substitution variable, equal that function. Well, we're going to do it different here. Okay, and we just have to remember for trig substitution, this is how we work. That is, I'm going to, rather than substitute, I'm going to think about, let's replace x with the variable theta according to this rule. X is a sine theta. So our x is our original variable. And instead of u, our substitution variable is going to be theta. We use theta because you can see it's inside a trig function, and maybe theta makes us think of angles. We actually could call it u. No one really does that for this technique. We use theta. And why in the world would we do such a bizarre thing? Like most students think avoiding trig is the right way to go when possible. And here we're going out of our way to introduce trig into an integral that doesn't have any present. Okay? So the reason we do it is because what it does for the radical. So let's take a look. All right, the radical here. I'm going to do a derivation, and then I'm going to come back over here and like fill in the blank what we can figure out about the radical. So the square root a squared minus x squared is equal to, under our substitution, a sine theta, that's x. And that is, just doing the algebra here, a squared minus a squared sine squared theta. And now take the a squared out and get 1 minus sine squared theta. And the square root of a product is the product of the square root. So the square root of a squared just turns into a. And I have left the square root of 1 minus sine squared theta. You should recognize that according to the Pythagorean identity. 1 minus sine squared theta is cosine squared. And now take the square root there, and we get a cosine theta. That goes up here in the blank. Cosine. So earlier I told you we call this constant a squared because a, its square root, is going to play a prominent role. And you see, I didn't mislead you. There it is. There it is. There it is. The square root, not a squared, but its square root. All right. Now, again, let me pause and set some. All right, so I went through the derivation for how the radical turns out using the Pythagorean identity. So we did that. We're going to remember what we did, and we're not going to derive it again. That is, we did the derivation, we understand. So in the future, when we see, let me go back to black, this radical, and we don't know how to get the antiderivative, then it should be automatic. We're going to replace x with a sine theta. The differential is a cosine theta d theta. And the radical turns out to be a cosine theta. So we immediately use these three things to rewrite the integral. And then there's only going to be sines and cosines involved. So like I said, it'll reduce it to an integral from the previous section. And hopefully we're experts at those. Let's try an example. The antiderivative of the square root of 9 minus x squared dx. Okay, this is not a terribly complicated looking function, but we actually don't know an antiderivative. We've never seen one before, so it seems like a good one to try this new technique on. So one thing good for you to do maybe is just pause the video and see if you can write out these three things. I'm not going to pause it. I'm going to move right ahead. The substitution we're going to make, we're going to replace x with 3 sine theta. And then dx is 3 cosine theta, d theta. And the radical becomes 3 cosine theta, as we showed earlier. And so therefore this integral becomes, the square root is 3 cosine theta. So replace it. And then all that's left is a dx. Well, that's another 3 cosine theta with a d theta. So take those 3's out, make 9. And we get the cosine squared of theta d theta. So is that any better? Do we know an antiderivative for that? And the answer is yes, we do. In fact, it's one that we derived in section 2, and you remember what I said about it? Memorize it. I said, because we're going to see it over again. And here it is, right off the bat, the first integral we see in the next section is cosine squared. So we know what to do. We memorized it. Of course you memorize it because I asked you to. So it's 1/2 theta plus 1/2 sine 2 theta. We'll add on our plus c at the end. All right, so there it is, an antiderivative. Unfortunately, it's expressed in terms of the substitution variable, theta. And we would really like to write it back in terms of the original variable, which we can do. So take our substitution relationship and solve it for theta. Divide by 3 and hit it with the inverse sign, the arc sign if you prefer. Okay, and now we'll plug it in. So I get 9/2 out front, and then I get theta, which is the inverse sine of x over 3, plus 1/2 the sine of 2, inverse sine x over 3. So there is a good answer. We can make it better. It's back in terms of the original variable. But remember what we talked about, simplifying these trig expressions. And here I have a sine of an angle. In fact, the angle is expressed as an inverse trig function, and it's actually a double. So this function right here, let me highlight it in yellow. That is not a trig function. And so if I want to go from a good answer to the best answer, I should write that as an algebraic function. We just did it, one like it, and so hopefully this will be nice and easy. Can't really do anything about that inverse sine of x over 3. But then, just like we did at the end, we use the double angle sine identity, which is 2 sine of the angle. The angle is the angle whose sine is x over 3 times the cosine of the angle. Right? The double angle identity, close paren. All right, so just a little more work here to clean this up. We get the inverse sine of x over 3. Those two's cancel. And then I get the sine of the angle whose sine is x over 3. Well, guess what? That's just x over 3. And then we draw our triangle for the cosine back here. So here's my angle. This is a right triangle. The sine of that angle is x over 3. Sine is opposite over hypotenuse. By Pythagorean's theorem, the adjacent leg is going to be 9 minus x squared. And then notice we need the cosine. So we're going to take adjacent 9 minus x squared over hypotenuse. And let's do one more thing. I guess let's push the 9 inside. I can see something good is going to happen there. So I get 1/2 9 inverse sine x over 3 plus, and notice when we push the 9 in, it cancels these 3's. So all that's left is, 1/2 is still out, so x square root 9 minus x squared plus c. So up here we've got a good answer. Down here we have the best answer. Okay? So let me write down what we've done here. It may have got lost in all the details. We started with kind of a not terrible looking function. And we asked, what is its antiderivative? And what did we get? Well, we got all of this. Like you'd never choose that in a million years. But evidently, assuming there's no mistake embedded there, and there's no big mistake, maybe it could be a little mistake, but basically that's the antiderivative. Okay, another example of just how much fun antiderivatives are. You can just never tell what's going on. All right, case 2. I guess we'll do it in blue. Here we have the radical a squared plus x squared. Or x squared plus a squared, however you want to write it. Okay, just like the last one, we're going to make a substitution. I'm not going to do the derivation. You can do it if you would like. It's all based on the reason we make it, and the reason why it turns out like it does is based on the Pythagorean identity. So in this case, we're going to replace x with a tangent theta. And the dx then is a secant squared. Take the derivative. And that will make the radical, thanks to the Pythagorean identity, a secant theta. Okay, and just like the first case, you need to get to a point where this is automatic. You see the radical? Possibly we could get the antiderivative by previous techniques, but if not, then we immediately go to trig substitution, and we don't rederive these. I mean, these are automatic. We know them. Okay? Which means maybe for you, in a few weeks, you write them on your 3x5 note card. So, here's an example I would like to do. The antiderivative of x squared over the square root of 9 plus x squared dx. So you look at that, and we don't know an antiderivative, so we're going to use trig substitution. We're going to replace x with 3 tangent theta, and that makes the differential 3 secant squared theta d theta, and it makes the radical 3 secant theta, thanks to the Pythagorean identity, which we didn't derive, but you'll trust me. Now, in the numerator, we have an x squared. Well, there's our x, so let's put it up there, 3 tangent theta. At the bottom, we have the radical, 3 secant theta. And then we have the differential, which is 3 secant squared theta d theta. Okay? Let's clean that up. These 3's will cancel. This secant goes away. One of those goes away. And we're left with 9, 3 squared, tangent squared theta, secant theta, d theta, which is an integral from 3.2. Presumably, we're experts. Because we've reduced it to a problem from the previous section, I'm going to stop here and go on to case 3 before this video gets too terribly long. So, case 3. Here the radical that we have is x squared minus a squared. And here we want to replace x with a secant theta. That makes dx a secant theta tangent theta d theta. And it makes the radical, thanks to the Pythagorean identity, a tangent theta. Okay, there's a technical issue with this. I think we're just going to avoid it, and we'll assume that these are the three things. And again, like before, we see this radical, and that's what we're going to do. Okay? Let's try an example. Go away. So here is the example. We'll go back to black. So there we have it, the same radical. We know no antiderivative, so we use our new method. We're going to replace x with 2 secant theta, which makes dx 2 secant theta tangent theta d theta. And it makes the radical x squared minus 4 equal to 2 tangent theta. So we rewrite it using the new variable theta. On top is the radical, which we've agreed is 2 tangent theta. On the bottom is x, which is 2 secant theta. And the dx is 2 secant theta tangent theta d theta. So we'll clean that up. 2's cancel, secant cancels. And we're left with, take the other 2 out, tangent squared d theta. Now, it may be that tangent squared, you think we don't know an antiderivative, and we don't, you'd be right. But it's really easy to get one. Again, using the Pythagorean identity, tangent squared, I believe, is secant squared theta minus 1. And now it's obvious in terms of theta. The antiderivative of secant squared is tangent. The antiderivative of 1 is theta. And now to get the original variable back, if I solve for theta, divide by 2, I get the inverse secant of x over 2. Okay? Now, inverse secant, I think on our calculators, it may not be built in. And I think I read somewhere on our online homework, there may not be an inverse secant function. But that's no problem. We can always convert it to an inverse cosine. Remember, secant is the reciprocal. So if theta is an angle whose secant is x over 2, then theta is the angle whose cosine is 2 over x. So all you need to do is reciprocate that. Then you can convert it to cosine. For us, it doesn't matter how we do it because we're not using a calculator. We can write it with either function. Right here, we get the tangent of that angle. I'll use secant just because it's kind of new. Minus theta, that's the inverse secant. And then we can simplify. Here's the trig composed with an inverse trig. We draw a picture. Here's the angle in a right triangle. The secant is x over 2, so the secant would be hypotenuse over adjacent. And then the other leg would be x squared minus 4. Notice that's the original radical, no coincidence there. And so I get twice. The tangent of this angle is 1/2 the square root of x squared minus 4, opposite over adjacent. And then we get minus the inverse secant. And maybe I'll write this one as cosine, thinking that our homework may recognize it better. And then we can write plus c, and we have our answer. So this antiderivative, there it is. Okay, over the weekend, I think I can do it on Saturday. I'm going to post another video with more examples, just for the practice. There are a lot of things that can go on here, and I want to talk about some of them. But this will allow you to get started on the homework. Good luck.